Thank you very much. That's right. I run the engineering team at Shell Street Labs. A little bit about myself as an introduction. I've been at Shell Street Labs for 2 years, dealing with the artificial intelligence part of things. Before that, I was at BFAM Partners, which is the main hedge fund that is behind Shell Street Labs. Before that, I've been on the sell side in the investment banking sphere for a while. So I came to Hong Kong in 2016 and worked for HSBC for a year and a half. And before that, I was in London for 15 years working for RBS and Credit Suisse at various places. So it's about 20 years of finance background. Shell Street Labs. How many of you have heard about Shell Street Labs here? So it's a few. Thomas, especially our AWS expert back in the corner there. It's been active since 2017, and it was created by Benjamin Fuchs that also created BFAM Partners, and CEO is Mark Nunes. He might show up later on tonight. We'll see. So today, I'm going to describe the companies behind this a little bit to start with. Then the core of the talk is basically about what powers AI technologies. So we're going through the life cycle, starting with where we get data, into where we do research, where Gautier would live, and then where we're training our models, and then where we deploy things in the kind of inference landscape. And that typically takes us into the hedge fund world. And then a few references for those that want more information about anything. If you're curious about anything, you can scan the QR code on the corner. That basically takes you to our YouTube channel where we have a bit of videos about things that we do. So first of all, BFAM Partners, we basically live across Victoria Park in 148 Electric Road. It's a multi-strat hedge fund. That means that we trade all sorts of asset classes. So it's both FX and equity volatility. So this is derivatives. We do a bit of credit stuff where Gautier worked with in the past. We do equity linked and rates trading as well. And basically, there are two types of trading. We do discretionary and systematic trading, which means that discretionary is when the traders decide themselves what to trade. So that is, they can base it on news in the media or their gut feeling. And systematic, which is basically rules-based. So that is things that are driven by algorithms. The big difference between Shell Street Lab and BFAM Partners is that BFAM Partners is regulated by the SFC. So things are a bit more organized, I would say, in the hedge fund. Shell Street Labs was, as I mentioned, established 2017. We work exclusively with BFAM Partners, also owned by Benjamin Fuchs. We are not regulated, which means that we can use whatever technology we want to do our work, which gives us a lot of freedom. And especially, we use AWS technologies, and this is the reason why I guess I'm here talking today. So first of all, the general principles that we use when we do use technologies is that we are very cloud-based, typically AWS to 90%. We use a bit of Azure as well. We use cloud-based technologies primarily because the nature is that we want to scale up and scale down. So we use sometimes a lot of compute, but we don't want to pay for that compute all the time. And then we also do not use much of SageMaker and other AutoML tools because most of our scientists like to write their things from scratch. And so we try to provide as much flexibility for the researchers to do work as they feel they are most productive. This is in contrast with BFAM Partners, which is a hedge fund, which is basically a money-making factory where things need to be a lot more stable. So it's more predictable. So starting from the back side, we have a number of data providers that we work with. Probably no secret that Bloomberg is one of the big ones. And we use a few other data providers as well, a bit of alternative data, but typically we feed our systems with financial data. We store a lot of it in S3, the bucket system of Amazon. It's pretty good for just storing data, I would say, and it's pretty cheap as well. Typically, we process that data using Lambda functions, which I will talk about a little bit in a second. But it works very well in combination with S3. And that typically triggers our ETL pipelines where we store data in more efficient manner, and that turns into other data storage systems like databases such as Redshift, RDS, and Aurora, which is the dynamic version of RDS, which I'll also mention a little bit more about. So this is typically what you see in the console. If you log into our AWS system, we have a number of databases, and you can pay attention to the Aurora versions, which says serverless. And that means that if we hitting the databases hard, they basically scale up, so we get a lot of performance. That consumes a lot more money at the time where we're using it, but then the researchers go back home and sleep, and it scales down, so we don't consume maximum amount of money all the time. So in practice, it looks something like this when we use various services on the AWS network. We have a certain number of savings plans because we know that we're going to use a certain amount of compute all the time. But sometimes we get spikes when we do trade models, or we pull out more data, or we load more data. So it's kind of goes up and goes down. So that's why we need the scalability. As I mentioned before, we use a fair amount of serverless technologies, which are called Lambdas in the AWS world. A very good framework if you use serverless technologies is the ones called serverless, as you see a screenshot on the right-hand side. It basically takes care of a lot of like the manual processes. So you deploy things with a one-liner, and it zips things up and ships it up to AWS, and you can even test run things locally, even though it's cloud-based services. So it's fairly useful, and it's only charging per 100 milliseconds of execution time. When doing research, we typically rely on Jupyter notebooks, as you've seen already, a few demos here. This runs on our Kubernetes cluster, which is also dynamically scalable backend. And we tend to deploy it using Terraform. Especially this is described quite a bit on the YouTube channel. So if you're interested in the technicalities around that, you can have a look at that channel. When it comes to training, we have a few different options. And as the previous speakers talked about how to scale things, we do scale things in various scenarios. So we basically use 3 different types of technologies to scale. In the most basic system, we use Kubernetes, which scales by default. This is quite handy for newcomers and the people that are not so technical. You're firing up a Jupyter notebook, and then you pick how much memory you want, and then off you go. Very simple. The people are a little bit more savvy, use GPU computing that we have heard about before. Just of interest, how many people of you have used GPUs? So about 30% maybe. And then for people that want even more power, they use HPC or high performance computing with AWS Parallel Cluster or Batch. So I'll talk a little bit about these technologies, each of them, and why you should use them and when you should use them. So how many of you have used Kubernetes? All right, 20% or so. So Kubernetes is basically a dynamically scalable technology for the cloud services, I would say, in general. They exist on all the main cloud providers. The Amazon version is called EKS, and they basically manage a control plane, which is basically the one that keeps track of all the management functionalities. And then you provision nodes under it, which takes care of the actual workloads. It's all quite automatic in the background. So when you need more computer resources, it has an autoscaler which provisions new instances, scales up, consumes more money, and generates more workloads. And then when you don't need it anymore, or you shut down all your notebooks, it shrinks back down. It's also schedules where to run workloads. So if you have some nodes where are very busy, then you will avoid scheduling new jobs on those. So it's doing a bit of interesting work in kind of moving things around. This is very handy when you're doing research, but you typically might not want that in a hedge fund where you don't want to lose trades or where things are critical. So it's good for research environments. And then GPUs, as some of you have heard, it's not very new concept, GPUs. I've been using GPUs or written GPU code since 1998 when I started working with virtual reality systems back at university times. People usually don't know so much about why we use GPUs. So I thought like it might be helpful with like a basic description. So what you typically see in any kind of modern computers today, you have a CPU and a GPU, and the CPU is the green thing that controls things. First thing when you're firing off jobs and you want to use GPU computing is that you take what you have in your normal memory and you ship it off to the GPU memory. And the GPUs has a lot of different cores. So typically a normal computer has things like up to 32 cores running things in parallel. But since GPUs come from the graphics background, you have thousands of cores instead. So it's very good at running things in parallel. So you can run a lot of jobs, but you need to ship the data first into the GPUs and you need to ship it back. So there is a cost of sending data into the GPUs and there's a cost of shipping them out. So it's typically good if you ship small amounts of data into the GPUs, do a lot of crunching and ship it out. So it's not always faster to run on a GPU, but it sounds good to run on GPUs because it's cool with GPUs. So I think it's. So why do we use GPUs? So this is an example of if you come into our hedge fund and you see what people do on a day-to-day basis. To the right-hand side is a trading application for equity derivatives that are written. We trade with this application with about 10 banks on a daily basis. And the reason for using GPUs in finance tends to be that there's a lot of computation going on in derivatives. So derivatives is when you can trade on assets that potentially you trade in the future at a certain price at a certain time. And pricing these can be a bit more computationally intense just because there's an infinite number of potential deals you can do. So in order to price derivatives, you typically create something called the volatility surface, where you compute the different prices for different scenarios that you look at. And this is where GPUs comes into practice, because you typically calculate what's known as the Black-Scholes formula, where you see on the right-hand side. And then you need to do that for all possible scenarios for the asset classes you trade. So if you come into our trading floor in BFAM Partners and you look at the traders' screens, you'll see a lot of curves, which is basically a slice of this volatility surface. And they're trying to see where things are mispriced. And then they send out this ticket you saw in the previous slide to the banks. And then the banks come back with quotes for whatever you ask the price for. And then you decide to trade with the ones that has the best price for you. GPUs are obviously good for machine learning as well, which is why we use them. And typically in the machine learning world, you use libraries. So it's kind of hidden away, but what you can do is that you can switch on the logging functionality, as you see on the little code snippet. And then you know that if things are actually running on the GPUs or not running on the GPUs. This, however, is typically not how I do it on a day-to-day basis, because this is just very super simple basic samples. So typically what we see on a day-to-day basis, it looks more like this. So this is our standard workhorse in Chelsea Labs, the Tesla T4 instances. They look like what you see to the right in physical shape, but typically what you see is the console on the left-hand side. So this is when we're training a cluster on GPUs. So what you see on the top is the 32 cores of CPUs. On the bottom, you see how much of GPUs are actually used, as well as temperature and other things. Another technology to scale things up is using HPC. And this is typically when you need a bit more power than just a single machine with some GPUs on. And this is when you want, say, 100 computers running and doing calculations for you. Then you can use either parallel cluster or AWS batch. We tend to be quite flexible, or I tend to provide whatever scientists like to use. So if you're a little more classical and you don't like Docker and new things, then you typically go parallel cluster. Otherwise, you go AWS batch. But to me, I'm mostly providing the engineering part of it. So, and then the scientists using it can choose a bit what they prefer. And finally, we're deploying our models after they've been trained. And this tends to be when we take in the step and moving things from Shell Street Labs into the hedge fund, into BFAM Partners. And in a hedge fund, you have a lot of surprises already. So you don't want too many technical surprises in that world. So that is typically where we lift our workloads from Amazon EKS, the Kubernetes side, and deploy them onto something like AWS ECS. We have a few different ways to deploy things, but I would say ECS is like the preferred way right now because it's very simple, very predictable, fairly cheap, and just fits the model of transitioning things from the research area into the production scenario. And finally, if you are interested in more the details of this and the technicalities, feel free to check out our YouTube channel, as I mentioned before. It shows a little bit more details about how we do these things. So this is typically Kubernetes and Terraform, which is infrastructure as code. And this is what we use when we recruit people. So we have something to talk about, and when we train our juniors. And I think that's all for me right now. Maybe there's questions around.